In high-stakes engineering, surviving by a microscopic margin isn't a success. It's simply a failure waiting to happen. If pressure shifts slightly, the system shatters. This diagram shows the foundational objective of binary classification. We have blue data points for a positive class and red data points for a negative class, separated by a linear decision boundary. We define it using the model f of x equals w dot x plus b. Any point falling on one side is classified as positive, and the other negative. Look at this specific blue point right here. It is technically on the correct side of the boundary. The model classifies it as positive and scores it as a correct prediction. But relying on that baseline accuracy is fragile. In real-world applications, data is inherently noisy. The slightest variance in a future measurement will push that point across the line, instantly turning a correct classification into an error. Reliability requires a physical gap. This spatial buffer between the data and the boundary is called the margin, a mathematical requirement for distance and confidence. Advanced margin-based classifiers, like support vector machines, actively punish models that draw boundaries too close to the data. They redefine success by enforcing a strict buffer zone. This table details how we translate that physical space into a quantifiable metric. We calculate the margin by multiplying the true label of the data point, y, by the model's prediction, f of x. Because the true label is always exactly +1 or -1, multiplying it by the prediction creates a reliable indicator. A correct prediction always yields a positive product, while an incorrect prediction yields a negative product. This leaves us with three possible states. Case 1 is our goal state. Y times f of x is greater than 1. The prediction is both correct and highly confident, sitting safely away from the boundary. Case 2 is the danger zone. The product is between 0 and 1. The prediction is mathematically correct but weak. The data point is lingering dangerously close to the dividing line. Case 3 is complete failure. The product is less than 0, meaning the point is on the wrong side of the line entirely. A robust model needs an algorithmic switch. It must ignore points in case 1, while aggressively penalizing points in cases 2 and 3 until they move into the safe zone. That mathematical switch is called Hinge loss. It is written as L equals the maximum of 0 and 1 minus y times f of x. The max of 0 operation creates a hard floor. It dictates that the loss can never drop below 0. There is no reward for being excessively correct. There is only a penalty for being wrong or too close. Let's run the math for case 1, where we have a strong, confident prediction of 2. We subtract that prediction from 1, giving us -1. The maximum of 0 and -1 is 0. A 0 loss means the model is perfectly satisfied. No penalty is applied. Now consider case 2, where we have a weak, unconfident prediction of 0.5. We subtract 0.5 from 1, leaving 0.5. The maximum of 0 and 0.5 is 0.5. The point is classified correctly, but because it is inside that buffer zone, the model still generates a penalty. If the prediction is completely wrong, say -2, we subtract -2 from 1, which equals 3. The penalty scales linearly, growing larger the further the point falls onto the wrong side. The constant 1 in this formula acts as an active repellent. It pushes data points away from the boundary until they cross the confidence threshold. We can map that mathematical threshold of 1 directly back onto our 2D coordinate plane. It creates two dashed margin boundaries, one at +1 and one at -1, running perfectly parallel to the main decision line. The entire space between these dashed lines becomes a literal penalty zone. Our case 1 point sits physically outside the dashed line. It exists in the 0 penalty safe zone. Our case 2 point falls inside the dashed margin. Even though it's on the correct side of the center line, the loss function actively pushes it outward. And our case 3 point lands completely on the wrong side of the center line, deep within the maximum penalty area. Hinge loss is simply a hard-coded mathematical translation of spatial geometry. If a point is inside the margin, it triggers a penalty. If it is outside, it is granted immunity. This brings us to the complete support vector machine objective function. The equation combines two distinct goals. The blue regularization term attempts to keep the model weights as simple and small as possible, while the orange hinge loss term strictly penalizes any margin violations. This specific combination creates a computational advantage known as sparse gradients. Because safe points outside the margin drop to exactly zero loss, they produce zero gradient. From the optimizer's perspective, they disappear entirely. The model only registers the support vectors, the specific points trapped inside the margin or classified incorrectly. This means SVMs are completely unbothered by extreme, distant outliers. The algorithm ignores them by default. This graph compares hinge loss on the left against logistic loss, or cross-entropy, on the right. Notice the difference in their shapes. Logistic loss evaluates probability. Because it asymptotically approaches zero but never touches it, the model will eternally push data points infinitely far away in a search for 100% certainty. Hinge loss, however, evaluates physical distance. Once a point crosses that hard boundary at 1, optimization abruptly stops. The model is satisfied. But this strict geometric approach introduces a significant mathematical problem. The hinge loss graph features a sharp, hard corner at exactly 1. Because of that sudden angle, the function is not perfectly differentiable using standard calculus. Standard gradient descent fails when it hits this corner. To optimize the model, engineers utilize a specialized mathematical tool called subgradients, which is exactly how we will train this algorithm in the next module.